Hello and welcome to Lecture 5, Introduction to the Solar System, and a deep dive into what makes the Earth so special. Today we will learn about the method of comparative planetology and how we use that to study the various objects in our solar system. We will also learn about the terrestrial and the Jovian planets, that is, the rocky planets and the gas giant planets. We will also learn about what makes Earth so special and how we have the planetary conditions here on Earth that we do. We'll also learn about atmospheric compositions and how atmospheric insulation can affect terrestrial planets. We will also see how Earth's geography and differentiated layers make it so special. And then we will apply what we can learn about life here on Earth and how it affects our planet to learn a little bit about astrobiology and how we could apply what we know about how life affects our planet to study other planets, these exoplanets, to potentially look for signs of life. In our previous lectures, we've gone over the history of the solar system and how our various discoveries helped inform our understanding of the solar system, how the various objects in it orbit, and eventually we've learned how it formed by studying these objects. So we know that our solar system has 8 major planets, many dwarf planets. I'm sorry if you think that Pluto is one of the major planets, but we will learn through these lectures and our comparative planetology that Pluto is actually a dwarf planet. It fits better in that category. There are also hundreds of moons in our solar system. Saturn and Jupiter each have over 60 moons. And there are countless other smaller objects, like comets and asteroids, which are all focused about our sun in elliptical orbits. However, despite this being a very complex system, astronomers have discovered that nearly all of these objects are connected and were formed together. Since many of these objects have very similar properties to each other, astronomers can group them together and use a method known as comparative planetology to study them in their groups based on their sizes and comparing and categorizing them. And they can actually use this to study all large objects in the universe based on their sizes and what categories they fit into. And the idea is that if two objects are similar, we can learn about another one by studying one. So if you've got a moon, we can learn about other moons by studying our own moon. And if we want to study potentially other planets that have life on them, well, we can study Earth because we can compare the conditions that we have here to what we could expect to find on other planets that could support life. One of the most important characteristics to compare when we're looking at celestial objects is their mass. The mass of an object can tell quite a bit about its origins and how it formed. So astronomers can learn a lot about the origins of our solar system by studying the masses of the different objects in it. So we believe that in the sun and all of the objects in the solar system formed from one spinning cloud of gas and dust that condensed down approximately 4.5 billion years ago. This mass was primarily concentrated in a central point, which we call the sun. The sun is 99.8% of the mass of our solar system. So it has enough mass to undergo nuclear fusion and become a star, but there are much smaller objects in our solar system because we still have that 0.2% to work with that makes up all of the planets and the comets and the asteroids and everything else. So actually, Jupiter makes up about half of that remainder mass that we're working with here. Jupiter is about 0.1% of the total mass of our solar system. It is our largest planet. And so the rest of the planets account for only 0.04 to about 0.09% of all of the mass in our solar system. The rest of the mass is in the form of these natural satellites like moons and rings and dust and anything much smaller than the planets that is still in our solar system. That accounts for about 0.03% of the mass in our solar system. So now let's go over the orbital plane of the solar system. All of the 8 major planets and many of the smaller bodies in our solar system all share a similar orbital plane with the Sun at one focus. Each planet orbits in the same direction on their elliptical orbit, with only a few minor inclinations deviating from this Sun's ecliptic, that similar orbital plane. Also, many of the planets have very similar low eccentricities in their orbit, with them ranging from 0.01 being a nearly perfect circle to 0.09, a little bit of an oblong circle. And then we have Mercury with 0.21, which is a little bit more eccentric, but that can actually be explained with general relativity. It did puzzle astronomers for a while, but once general relativity's effects were included on for Mercury being so close to the mass of the Sun, Mercury's orbit is actually perfectly in line with it makes sense being that eccentric. But all of this to say, this suggests that many of the objects in our solar system formed at roughly the same time, and they were all focused gravitationally about the Sun. However, some objects in our solar system don't quite orbit in the same way, and this makes them unique in our methods for comparative planetology. So when we look at the picture on the left, we can see that many of the planets orbit in these nice elliptical orbits that are on the same plane. We see that the major planets in blue on the orbital plane it being in blue. And then we can see that the dwarf planets in red, quite a few of the ones that are further away are very deviated off this orbital plane. We can see that Eris is very off of the orbital plane, and then we can see that Pluto also is a little bit off, which was one of the signs to astronomers that Pluto didn't quite fit into the group of planets and needed to perhaps be in its own category, the trans-Neptunian objects. So our first group that we're going to look at with our comparative planetology are the terrestrial planets. These are the 4 planets that are closest to the Sun. They all have very similar compositions. Our Moon also has a similar composition to these terrestrial planets in that they are all relatively small compared to the gas giants, but they are larger than the dwarf planets, and they are composed primarily of rock, silicates, and metals. What makes terrestrial planets is unique is that since they have rocky solid surfaces, we can examine these surfaces for their geological activity and features that tell us a bit about how they evolved over time and how they were formed. So the structures of these terrestrial planets are quite similar, with each one of them being composed of different amounts of silicates and metals, with iron being the main metal, and this ultimately determines their mass based on what their composition is. Among these terrestrial planets, Venus, Earth, and Mars are the most alike, with having about 1/3 of their mass as iron nickel and iron sulfur, and 2/3 of it being silicates with oxidized crusts. All the terrestrial planets have also been differentiated. This is the process through which gravity separates the materials in a planet into different layers based on their density. This implies, though, that since the planets are mostly solid today, that they once had hot liquid layers before cooling. This is what would make it much easier for these layers to differentiate and give rise to what we see today. So how do terrestrial planets get shaped the way that they are? Well, we can see that a lot of them, like on Mercury and our moon, they bear the hallmarks of billions of years of collisions from asteroids and meteors, and some of these collisions were large enough that some of these rocky planets even have a little bit of axial tilt. They got hit so hard that it knocked them off their axis a little bit. But external forces are not all that can affect the surface. There are also internal forces and geologic activity, which are constantly shaping and twisting and buckling the outer crusts of these terrestrial planets to create different formations and reshape the entire surface. This geologic activity is the result of primordial heat. That is the heat that was left over during a planet's formation when it was in that hot, dense cloud in the early solar system. But that heat remains because it trapped due to the insulation of the crust and the material, and so the hot cores are still there with the heat trapped in by the outer layers, and in the case of some of these planets, also by the atmosphere of the planet. As we move further out in our solar system, we come to the Jovian planets, these giant planets. And these are what we can call the gas giant planets. They are comparatively large to the terrestrial planets, and they are composed mostly of hydrogen and helium, much like our sun. Since they are composed mostly of gases, they lack a solid surface, but instead have very thick atmospheres of gases and then vast oceans of condensed liquid hydrogen, which surrounds much smaller, dense cores, which were formed in processes similar to our own sun. The largest giant planets, Jupiter and Saturn, are made up of mostly hydrogen and helium, with them being about 75% hydrogen and 25% helium. And a lot of this are compressed into very unique states when they are in such dense conditions. In fact, surrounding their cores is actually metallic hydrogen, which is a state of hydrogen which has similar properties to metals and solids when it's so dense. The two smaller gas giants, on the other hand, Uranus and Neptune, were less efficient at attracting hydrogen and helium since they were smaller, and are in what we call a reduced state because they have a lot of ice. Many giant planets, not many, all of the giant planets have very dense cores in differentiated layers, and since Uranus and Neptune didn't have are much lighter and have less hydrogen and helium, their cores are comparatively larger than their surface area in their atmosphere. So now we move on to the smaller objects in our solar system because not only are there these large planets, but there are many, many more smaller objects. So a lot of the planets and even some of the dwarf planets have moons orbiting them. The Jovian planets even have orbital rings. We all know Saturn has a ring, but also all of the other ones do too. Jupiter has a tiny ring, Uranus has a tiny ring, and so does Neptune. It's just that Saturn's is much larger and much prettier, so it takes all of the ring fame. There are also the asteroids, which lie in the asteroid belt between Mars and Jupiter. We have comets, which live out in the Oort cloud. This is a large cloud about 1 to 2 light years in diameter around the sun, which is filled with comets that are each on very eccentric orbits that cause them to occasionally whiz by the sun real fast and light up our skies. Since comets are composed mostly of frozen ices, as they get closer to the sun, they melt and they produce these long, beautiful tails, which give us these beautiful displays in the sky when we can see them when the comets actually are real nice. I know that my parents still talk about seeing Halley's Comet back in the day. I know we'll have to wait a while to see that one, but hopefully we'll get a nice comet in our lifetimes. There's also many, many more smaller bits and countless bits of grains of cosmic dust that fill our solar system and occasionally enter our Earth's atmosphere in the form of meteorites. And there's also a lot of frozen, icy, smaller dwarf planets out beyond the orbit of Neptune, which we call trans-Neptunian objects. When we look at the largest moons of our solar system, they are actually comparable in size to some of the smaller planets. We can see on the image on the right that a lot of the moons are actually our own moon is larger than Pluto. And Ganymede is larger than Mercury. So there some of the moons are actually much larger than the planets. And this was one sign that Pluto wasn't quite a planet. There's more to a planet than just its surface. All of the planets in our solar system have atmospheres. So even Mercury, which is very small, has a tiny, tenuous atmosphere around it, which does an all right job of holding in heat. But as we look at the other terrestrial planets in our solar system, like Venus and Earth, that have much thicker atmospheres, we see that their atmospheres are very good at insulating the surfaces. And this is a way that the light and the heat from the sun is absorbed by the planet's surface, and is then re-emitted as infrared radiation, which is then actually trapped by the gases in the atmosphere, thus holding the heat in close to the surface of the planet. This effect is what we call the greenhouse effect. And it is really prevalent on Venus because Venus has a thick atmosphere of carbon dioxide, and so its atmosphere actually insulates the heat in so well that Venus's surface is hotter than Mercury's, even though Mercury is closest to the sun. And Earth's atmosphere keeps us just warm enough that our oceans don't freeze. So that's also really important and really cool. So now we have made it to Earth. Earth is the coolest planet in the solar system because it has you all. And you are all awesome. But actually, Earth is really unique in the solar system because it's the only planet that contains life. And life does some really cool things to our planet's surface. But in addition to life, our surface is also very active geologically. This means that we have very few visible craters. And while we are impacted about the same rate by space debris and rocks as the other terrestrial planets, our geological activity actually hides and erases a lot of these craters. And this means that we have to really dig deep, so to speak, to find evidence of past impacts that aren't as visible. Earth is about a medium-sized planet as far as the terrestrial planets go, and it has a radius of 6,378 kilometers with a mass of about 5.98 times 10 to the 24 kilograms. It weighs quite a bit, and it's composed primarily of heavy elements like iron, silicates, and oxygen, which are relatively rare compared to the rest of our solar system. The mass of the Earth really helps us understand how it has its structure, how it has these differentiated layers, and it also tells us about where the heavier elements are based on our composition, because our overall density for Earth is 5.514 grams per cubic centimeter. And all of this adds up to a really dynamic planet that has a lot of changing conditions and atmospheric conditions and geological conditions. And all of this adds up to the perfect conditions for life. So the Earth has a magnetic field that extends through our poles, the North and South Pole. We can picture the Earth kind of like a bar magnet in this way. And so we've got these regions around the Earth in our magnetic field where charged particles move along. This is known as the magnetosphere, and it was discovered in 1958 by the first satellite that the US launched. These charged particles are trapped in our magnetosphere, and they mostly originate from the sun from the solar wind. So the sun is constantly sending particles out into space, charged particles like protons and electrons, and this is what we call the solar wind. And these charged particles are attracted to the magnetic field lines on the Earth. Some of them then are pulled along the magnetic field lines, and these are actually what give us aurora. Loose collection of particles and gases around the Earth is what we call our atmosphere. This is what we breathe and is responsible for keeping our surface temperature, this lovely temperature that is perfect for life. And most of our atmosphere is closest to the surface in the troposphere. And this is where the weather occurs, where there's a lot of air circulated by convection. Above that is the stratosphere, which is above the clouds. And the final layer of our atmosphere is the ozone, where there is very heavy oxygen ions or oxygen molecules, this case oxygen 3 compounds, which absorb a lot of harmful UV and help insulate our surface temperature. And the remaining layers are the mesosphere and the ionosphere, and they are much less dense and they primarily interact with the charged particles, and this is where aurora occur up in the atmosphere. And they are also where the lighter elements are present, whereas the heavier elements are much closer down to the bottom. So the Earth's atmosphere is composed primarily of nitrogen, oxygen, and a little bit of argon, with a few other gases in there, primarily water vapor and carbon dioxide. So our atmosphere is a very good insulator, and this is what gives us that greenhouse effect. So we can see in the graphic on the left side, we can see that light from the sun is then it arrives at the Earth's surface. It is absorbed by the Earth's surface, and it is then some of it is reflected back into space, but some of it is absorbed and re-radiated as heat. And a lot of that heat is then trapped by the greenhouse gases in our atmosphere. And this acts as a blanket and keeps our planet warm. Without this greenhouse effect, we would actually freeze. But there has been a little bit of unnatural development in our atmosphere, and now we actually have very large excesses of CO2, and our greenhouse effect has actually started to increase, and our planet has been consistently warming, tracking with the Industrial Revolution and human activity on the planet. So now we're going to talk about the weather and the climate. These sometimes are used interchangeably, but they mean different things. And so, us as scientists, we want to use these words correctly. So, weather refers to the convection under the Earth's troposphere, which is where we have most of the atmosphere and the atmospheric events. So, this is weather is the day to day action of the convection in the troposphere. But weather is different from the climate. Climate refers to long-term and widespread effects of the atmosphere, and climate is what weather results from over many years. So climate changes have been recorded throughout history, such as ice ages, when the temperatures in the northern hemisphere significantly shifted due to axial changes in the Earth's rotation. But there's also been long-term atmospheric changes caused by human activity on the planet, specifically our industrial activity and our emission of greenhouse gases like CO2, and this has greatly affected our climate. This is something that we can see today and will have an impact on us far into the future. The interior of the Earth was once much hotter, and it was once in a molten state, and this is what led to our differentiated layers. So how do we know this? Well, one of the ways that we can indirectly measure the composition of the interior of the planet is through seismic waves from earthquakes. So there are two types of waves, S and P waves. This is a little bit outside my expertise, but essentially We can tell the composition of the interior based on the type of wave that we measure as it passes through different parts of the planet. So when we look at our graphic on the right, we can see that if you are directly across the planet from an event, so it has to go through the core, you're only going to feel the P waves. S waves are going to travel through the crust much better than they would travel through the cores or the inner cores, for instance. So this is one way that we can probe the composition of the interior of the Earth through seismic wave transmission rates. And this is how we can create a seismic image which models the distinct layers of the Earth based on the differentiation from how the waves travel through these different layers. The Earth is divided into four distinct layers based on our seismic imaging of its interior. The top layer, the surface layer, is called the crust, and it is divided into the oceanic crust and the continental crust. Oceanic crust is produced by cooling lava and is made up of heavier elements than continental crust. Continental crust is composed primarily of oxidized silicon rocks. The crust is relatively low in density and only makes up a little bit of the Earth's mass, with being less than 1%. The largest layer of the Earth's composition is the mantle, which stretches as far as almost 3,000 kilometers below the crust, and it is a little bit less solid. So this means that the rock is a little bit deformed and not quite solid, and it can flow a little bit. We're in this in-between solid and liquid state down here. And below the mantle is the metallic core, which is divided into the inner and outer core. The inner core is solid and composed of the heaviest elements, while the outer core is more liquid and composed of denser elements than the mantle, which is like the irons and nickels and sulfurs. Because of convection currents in the mantle and breakages of the crust, the Earth is divided into a dozen plates that we call tectonic plates. So while there are tectonic forces on all of the terrestrial planets with active geology and some primordial heat, Earth is the only terrestrial planet that has plate tectonic forces. Plate tectonics and their interactions at the boundaries between the plates make Earth's geography very unique in the solar system. And this is what gives rise to our constantly changing surface. There are several ways that these plates can interact. Plates can pull apart in what we call rift zones, where these gaps are then filled with lava and we can generate more surface. There's also subduction zones where these plates burrow against each other, and this is when one plate is forced under another one due to the pressure produced at a rift zone. And this causes the plate material to be recycled. So that's pretty cool. We're kind of reusing parts of our surface. That's pretty cool. We're recycling. We also have parallel sliding. This is faults at the plate boundaries, and this causes earthquakes when the plates laterally slip and slide past each other and release energy. There's also direct collisions between plates where they push into each other, and the direct force causes some buckling of the crust, and this is how we get really tall structures like hills and mountains. When we study Earth's surface and its crust, we find three types of rocks. We have the igneous rocks, which were formed from minerals cooling from a molten state. This is our volcanic rocks. We also have sedimentary rocks, which form from fragmented bits of igneous rock and organic byproducts like shells and fossil materials. And these are deposited together by nature and cemented together over time by pressure. There is no melting involved in sedimentary rock. Metamorphic rock refers to rocks produced at high temperatures and pressures of igneous and sedimentary rocks undergoing physical changes. So metamorphic rock is the types of it's like igneous and sedimentary rock that then had to undergo high temperature and pressure to then become a unique type of rock. There is another hypothetical type of rock, and this is primitive rock. This is rock that was formed from the sun and when the planets were forming, and is rock that did not have any interaction with Earth's geological activity. So we now know, since Earth is very geologically active, there is no primitive rock left on Earth to study. So we can only study it by sampling terrestrial objects which have not experienced geological activity, like asteroids, comets, and smaller moons. The thing that makes Earth so special is that we have life, and life affects planets in its how they exist and how they develop. So the study of how life affects the evolution of a planet is called astrobiology. Astrobiology can be used to chemically study the records of life and evolution on our planet. So from the evidence of the oldest surviving rock records, we have little rocky colonies called stromatolites, which are here on Earth still today. And these stromatolites were caused by a bacterium called cyanobacteria. And so these provide a little bit of a geologic and fossil record for the earliest stages of life. We know from chemical studies of the Earth's atmosphere back then that it lacked oxygen until cyanobacteria evolved and were able to produce oxygen. And so the cyclic evolution of Earth's atmosphere with life and with the geological processes on it is very messy, and we think that there were probably countless repetitions of life forming over and over again before a life form finally persevered and was able to survive permanently and keep our planet inhabited. Changes in our atmosphere started to occur about 2 billion years ago. So, despite the existence of plant-like organisms that can produce oxygen through photosynthesis, a lot of that oxygen was removed by chemical reactions in the crust before it could be freed to the atmosphere. So, this changed after a sequence of evolution in blue-green algae, the cyanobacteria. Cyanobacteria evolved to use photosynthesis more efficiently, and they would take carbon dioxide from the atmosphere to produce oxygen, and this led to abundant amounts of oxygen in our atmosphere. And over time, the ozone layer was formed from molecular oxygen and protects the Earth's surface and helped allow for new complex forms of life to evolve on our oxygen-rich surface. However, the existence of these life forms resulted in less CO2 in the Earth's atmosphere, and this helps distinguish it really greatly from the other terrestrial planets in our solar system, which have rich CO2 in their atmospheres, like Venus and Mars. We don't have as much CO2 in our atmosphere because we have life on our planet, which is changing our atmosphere's composition. Life is not the only thing which influences our planet's surface and conditions, but also there are external forces and collisions which really impact our planet, and these actually happen at a roughly uniformly constant rate. Fortunately, small debris does not pass through our atmosphere because it burns up due to the friction as it passes through all of the gases in the atmosphere, but large debris is not stopped by this effect and can impact the surface. So many of these impact scars have been erased by geological activity, like erosion or weathering, or even being subducted down into the plate from plate tectonics, but some evidence still remains. So one of the most recent impact events happened over Russia in Chelyabinsk, Russia, where there was an air blast from a meteorite or a meteor impact in the atmosphere, which released a shock wave equivalent to half a megaton of TNT. And that was a relatively small rock that produced that air blast. The best known crater is Meteor Crater out in Arizona, where a 40 meteor iron projectile hit our planet about 50,000 years ago and produced a really, really spectacular crater. And since then, we have found over 150 historic craters around Earth. One of these impact events is what wiped out the dinosaurs. These impact events have a huge effect on life on Earth, which we will see more of in the next slide. Meteors and their impacts on our surface can be some of the most influential events on our planet. So, nearly 65 million years ago, the Earth took a huge impact from a meteor, and this marked the end of the Cretaceous period when it struck the Yucatan Peninsula in what we call the Chicxulub crater. This wiped out nearly three-quarters of all plant and animal life on the Earth, and the collision released more than 1 trillion tons of sediment into the atmosphere. And this had from the collision, which was about the size of 5 billion nuclear bombs. That sediment went into our atmosphere, blocked out a lot of sunlight and heat and radiation, which then further led to extinction events. This crater is marked now by a shallow sea, but it was nearly 200 kilometers across at one point. Evidence for this event was found in 1979 due to iridium compounds found in the sediment layer around there. Iridium compounds are incredibly rare on Earth, but very abundant in asteroids and comets. So this was one indication that in the past there was an impact from a space originating object on our surface. But these impacts and potential mass extinction events aren't necessarily events of the past. We currently have government agencies like NASA's Space Guard Survey, which is constantly monitoring the sky for potential cosmic impact hazards. I believe that there is actually a small asteroid that was found that has about a 1% chance to impact the Earth in the year 2030. 1% chance is pretty small, but that's actually currently the most threatening object out there that we know of. There could be more things out there that we just haven't seen yet. So we constantly need to have these programs monitoring the night sky, looking for asteroids, and calculating their trajectories so that we can make sure that the Earth is safe. We have a couple programs in place that are theoretically capable of protecting the Earth. We have deflected an asteroid's trajectory with the DART mission before, but we don't know if that will be enough to protect us from such impact events in the future if we can't detect them in time. We have now reached the end of this lecture on the solar system and using comparative planetology, and also what makes the Earth so special.